Question 24 here on the math subject GRE practice test. What we're asked is which of the following sets of vectors is a spanning set for the null space of this matrix. So first off, the null space. All the null space is the collection of vectors that this matrix maps to the origin. So if this language of linear algebra confuses you, you can kind of think about it as just the solutions to a set of linear equations. So if I call my variables x, y, and z, this top row of the matrix tells me 1x plus 3y minus 2z would be the x coordinate of my new vector. And since I'm interested in the vectors that get mapped to the origin, well, the origin has an x coordinate of 0, so I'm going to set that equal to 0. Similarly, this second row tells me that 2x plus 1y minus 1z gives the y coordinate of the image. And again, I want that to be equal to 0 because we're getting mapped to the origin. And then finally, the last one says negative 4x minus 2y plus 2z gives me the z coordinate of the image. And so I set that equal to 0. And if I can solve this system of linear equations, it'll tell me which vectors get mapped to the origin. In other words, what the null space of this matrix is. You can solve the problem this way if you want, but matrices give you a nice little shorthand for this. So what we'll do with this matrix is append one extra column, a column full of zeros. That augmented matrix will be the one that gives us the null space. Maybe I'll write this down here. So here's the matrix that I want to reduce. To get it into reduced row echelon form, I already have a 1 in this spot, so I'll probably just leave this top row alone for now. I want this to be a 0. So what I'll do is I'll take this row and subtract 2 of the top row. So 2 minus 2 1s gives me a 0. 1 minus 2 3s is 1 minus 6, or negative 5. Negative 1 minus 2 negative 2s is negative 1 minus negative 4. In other words, negative 1 plus 4. In other words, 3. And 0 minus 2 zeros is just 0. If it helps you keep track, this is the old second row minus 2 of the old first row. Same idea with my third row here. I want this to be a 0. So I can either take my old third row and add 4 of my first row, or take my old third row and add 2 of my old second row. I'm going to do that latter thing because not only will that make this a 0, it'll also make this a 0, and this is 0, which is kind of nice. All right, row 3 plus 2 of R2. Negative 4 plus 2 2s is 0. Negative 2 plus 2 1s is 0. 2 plus 2 negative 1s is 0. And 0 plus 2 zeros is 0. Because I have this row of zeros, I know that I'll have a free variable. I'll be able to choose whatever I want for z. You could stop right here and switch back into equations to solve, but I'm going to take it one step further. I'm going to use this negative 5 to put a 0 in this space. So the way I'll do that is I'll take 5 of my first row and then add 3 of my second row. So 5 1s plus 3 zeros gives me 5. 5 3s plus 3 negative 5s gives me 0. 5 negative 2s plus 3 3s gives me negative 1. And 5 zeros plus 3 zeros gives me 0. I'll leave my second row alone for now. I've now got as many zeros as I can get. Maybe I'll scale these so that my leading entries are 1s, and then call my matrix good. So divide this one by 5. I got 1, 0, negative 1/5, 0. Divide this one by negative 5. I got 0, 1, negative 3/5, and 0. And then I still have my row of zeros down at the bottom. If you think about the connection between matrices and my system of equations here, what I've just figured out is that this system of equations is equivalent to the system of equations represented by this matrix, which would just be 1x plus 0y's minus 1/5 z equals 0. And this second row, I got 0x's, 1y minus 3/5 z equals 0. So if you stare at these equations, you can kind of tell that like z can be whatever you want, and then based on what you choose for z, you'll choose x and you'll choose y. So one non-zero solution to the system of linear equations would be if we let z be equal to 1. If z equals 1, then it looks like y would be positive 3/5, because 3/5 minus 3/5 times 1 equals 0, and x would be positive 1/5, because 1/5 minus 1/5 equals 0. But this is just one solution to this system of linear equations, right? And because we can choose whatever we want for z, there's infinitely many solutions. But maybe you can kind of see what would happen as we change z, right? If we chose z to be equal to 2, then this would just be 6/5, and this would just be 2/5, right? As we scale z, we scale x and y accordingly. What I'm saying is really we get a solution from any scaling of this vector right here. Typically, this is written with like a t out in front. That's kind of the parameter. And we can choose whatever we want for t other than 0 and get our basis vector. That basis vector will be our spanning set, and we'll be done with the problem. So you're like, okay, so you have your answer, 1/5, 3/5, 1, because I don't see that anywhere up here. Well, if you look at this question really carefully, it says, which of the following sets of vectors is a spanning set? There's infinitely many spanning sets. Again, any multiple of this vector will work. So if you look at your answers, what you got to ask yourself is which of these is a multiple of this? Well, if you look at B right here, looks like they took this vector and just let t be equal to 5 to get rid of all the fractions. 5 times 1/5 is 1, 5 times 3/5 is 3, and 5 times 1 is 5. So a spanning set for our null space would be 1, 3, 5. Maybe the spanning set for our null space would be t times 1/5, 3/5, 1, or 1, 3, 5. Anyways, the answer is B.